California aqueduct is an incredible construction, a super highway for water that stretches over 400 miles across California. Just incredible. But this man-made river was hiding secrets that I finally uncovered. This part of the Mojave Desert has been graced by some incredible aircraft. It is home to Edwards Air Force Base and a few other installations. Nearby, we have the spaceport. I spent decades supporting the defense industry, and towards the end of my career, I got gripped by the strangest ideas of all. The possibility that the Earth is actually flat. Very strange. In retrospect, it was inevitable. I had seen too much. I moved around, worked on so many different projects across the country, and I've seen things I couldn't explain. And then all of a sudden they started making sense. It was the flat Earth. In grad school, I researched electromagnetics, and I soon found out this skill was highly sought after by defense contractors. And so I had a blast jumping from contract to contract, going from one end of the country to the other. Life was great. And then one day I got a call. They wanted to interview me for a directed energy job, and some folks from around the Pentagon called, and I had a good chat with them, and they said, okay, somebody will contact you from HR and bring you for an interview. I was enjoying my time in Florida and kind of had mixed feeling about changing jobs, but anyway, since these people called, I said, yeah, let me see where this goes. At least I'll get a free, trip, go for an interview. So the next day, this lady calls and she says, when can you come to Las Vegas? And I went, what? Las Vegas? I thought you guys were in, somewhere around the Pentagon. I just talked to some guys. And she said, I don't know anything about that. I was just instructed to bring you to Las Vegas. I thought, oh God, I know exactly what this is all about. I watched the History Channel. Anyway, I lasted only a few years. Quite demanding work, takes a lot of time out of your day, and I have nothing but respect for all the people that support out there. And I couldn't wait to get off the range, but that experience ushered me into the world of electronic warfare and signals intelligence. A few years later, at a different job, one day a fellow engineer retired, and they couldn't find a replacement, so they asked me if I wanted to go look after this simulator and make sure it's calibrated. So I said sure. I was an RF engineer and I jumped at the opportunity. And that's the first time I saw the words flat earth right there on one of the first dialog boxes that opened up. There was a checkbox. Do you want a flat earth or not? And I thought, what? That's very strange. Why in the world is that there? Around this time, I clicked on my first flat earth video in YouTube, and I was like, what? This is crazy. Do people mean the earth is flat not locally but globally? I mean, instantly you're thinking, what? That doesn't make sense. What? That's kind of crazy. So I started to talk to my fellow engineers and kind of joke around, a bit tongue-in-cheek, and I used to tell them, hey, NASA is hiding the flat Earth with fisheye lenses. Yeah, they're doing it on purpose. And, so this kind of went on for a little bit, and we were also analyzing data from our payloads, and one of my friends, I remember, he called me over and said, hey, come check this out. We were testing a payload, and we're receiving signals, and one of the air route surveillance radar was picked up, and of course, this is standard theory. You can move about and you get different direction to signals, and then you can triangulate your location, standard direction finding techniques. Anyway, he was processing all this data, and he didn't filter. Usually we filter because we're interested in signals, in the vicinity. But he didn't filter anything, and all of a sudden he picked up signals like way out there, almost, if I remember correctly, 2 times the distance to the horizon. And this graphic is exaggerated. I'm just showing you this graphic. I don't want to reveal any sensitive information, but yeah, the green line kind of shows the direct line of sight. So how can you pick up a signal around the curvature of the Earth? And I was like, oh my goodness, we got data at our fingertips. Oh my God, and that's when I got really interested into what was going on. What is this flat Earth phenomena? So radar waves bend. That's the standard theory. That's what everybody talks about. But I started to get a little bit more curious, and I was doing a lot of thinking. I started reading papers. One of the first papers I read was this one, Measurement of Variations in Atmospheric Refractive Index with an Airborne Microwave Refractometer. And I highlighted in red their introduction. Experience shows that meter and centimeter length electromagnetic waves are propagated far beyond the horizon, with a field strength much greater than what can be accounted for on the basis of standard diffraction theory. I was like, well, I have that experience. I'm seeing it in my data. And I was very, very intrigued. I looked at patterns of this circuitry, and did a lot of research into anomalous propagation. There is ducting and radar holes, etc. And this phenomena can be beneficial to the military. One thing I quickly realized is that some studies just reference the Earth's surface. And I said, no. You have to prove that it really bends. Measure that index of refraction. And it's really a hard problem. But, just simply detecting a signal out there with a known, coordinate, and then doing this kind of geometry and saying, well, because we detected so much farther out, that means radar had to bend. It's not real science. You're just using one theoretical model to support another one. You have to prove absolutely that radar has actually bent. And just like that, slowly, all these anomalies that I had seen in my career came to the surface. I'd suppressed them. I remember in the 90s, some guy was trying to interest me in working on this program, and we were in the cafeteria, and he was saying, this aircraft is so cool, and we can pick up jets flying over Cuba. And we were around Dallas, And I thought, yeah, that's what radars are supposed to do, I didn't think much of it, Yeah, they're designed to pick up jets flying over Cuba. I should have jumped to that knowledge, but that illustrates how tired our minds really get. Education in many ways has failed a lot of people. There's just too much knowledge out there, Our brains seem to be of limited capacity, and, people that pursue higher degrees, like I did. I mean, you specialize in a specific area, but there's just so much out there, and, very hard to comprehend. You need multiple lifetimes to, gather all this. But once in a while, people are beginning to wonder, and that's how you wake up. The key is to question everything, but not all the time, right? We don't go around questioning whether gravity pulls us downward. Experience tells us, yes, okay, that was settled. It was the same thing with the Earth, I mean, so much is based on the Earth model and, astronomy and other things. So we don't go around kind of, resurrecting that debate, but there's a phenomena going on right now. Everybody on YouTube seems to be talking about the flat Earth, and it kind of gripped me, and I said, I've seen things that correlate. This is fascinating. Then somebody sent me a paper, and I didn't quite like the tone of it. It was a Sandia National Labs report, written by somebody that works in intelligence, surveillance, and reconnaissance like I did. And in the abstract, the first sentence caught my attention. It says, the Earth isn't flat and radar beams don't travel straight. So categorical. That just bothered me, That really bothered me. I said, man, there is something to this flat Earth phenomena. We gotta get to the bottom of it. And that's how I started doing experiments in infrared to, measure the radius of the Earth. And I had these other things in my head that I can't quite talk about that I've seen in my profession. And slowly I awoke to the flat Earth reality. But I wanted to measure the Earth in the visible spectrum. I was going on the assumption that there is upward refraction that's bending the light. That's why things appear to disappear over the horizon. They appear to disappear over the horizon. And it's because it's gotta be upward refraction, and it makes sense because there's a temperature gradient. So I said, this has to be it, It's really just crazy. In one model, you're seeing far because light bends around the curvature of the Earth because you think it's curved. In the other model, you're saying, well, the Earth is flat, and the reason I don't see in the distance is because light is curving up. And this model makes more sense because when you look way out in the distance, you're looking at shallow angles, and that's where the bending is more pronounced, as you will see. And going based on this idea, I began to do all these experiments in Antelope Valley. This area is extremely flat, and I designed a test to take advantage of this flatness. Using a theodolite, I can measure the elevation angles to a distant target, an antenna on top of a mountain, a rock outcropping, etc. And then I can calculate the height to the mountain if I know the distance to that object. And I'm interested in the relative height. I'm not really interested in the absolute relative to mean sea level. What I'm after is to see if the gravitational vector is varying and by how much. Now this assumes no light bending, but in actuality there is light bending and things get more complicated. Just 1 mile from the freeway, I found a nice, somewhat quiet street, and I started doing measurements along a direction of north-south. So now I am by the sign here, Avenue G. So before we were out there by that building. There's Apollo Park again. So I just drove. I think the distance between these roads is about 1 mile. So we'll look at Google Earth and get an actual distance. So this is just an example of one of the measurements that I've made out there. I'm not going to show you everything. This video will get too long. The process is very simple. You level the tripod and then you align it and you read the measurements. And I did both forward and reverse measurements to minimize the error. And I'm sighting a building right next to that antenna. And it was clearly visible, a good target to align to. Here's the results of the first data set. The results are very intriguing. I measure the radius of the Earth between segments, and sometimes it's way above and other times it's way below. I also kept track of the time and I correlated to a temperature graph from the city nearby, and started to wonder whether me jumping around, as you can see in the time column, not everything is in a consecutive order. So still, I was puzzled by the jump between point 1 and 2. The measured height of the target varies by 40 feet. That's just incredible. We're moving along a somewhat flat surface here that doesn't vary by more than, plus or minus 1 foot maybe. At most, and we're measuring a 40-foot difference. Wow. Let's have a look at 3 models that will get us thinking about what might be happening. The first model is a ideal flat Earth model. If you think about it, the surface is flat, the vectors shown in blue, the gravity vectors are parallel to each other, and there's no refraction. And under this ideal condition, as we move our theodolite from one position to another, and we measure that angle theta, the elevation angle to the target, right, should produce the same height of the target. But as we saw, we're not getting the same height. So something is going on. Either there's refraction or those parallel gravity vectors are bending. Or maybe both. In the second model, we introduce light bending or refraction, and it has to be upwards. Look at the blue line, it's curving up, okay? And this actually can explain the results, because from a distant location at D2, we measured the lower height H2 along the dotted red line, which is the geometric line of sight that we imagined in the calculations. So this is actually a good model, and it has a lot of merit. However, if the gravity vectors are bending, because we're on a curved surface, that also can explain it. And that's illustrated in the next model. In this model, we have a curved surface shown in blue and no refraction. If the surface is curved, then the gravitational vectors are not parallel and they diverge from each other. Thus, the theodolite is leveled at slightly different angles at the two locations because the gravity vectors are different. And so you can see there we're measuring different height relative to two different ground plane references. And I showed the equation how I calculate the radius of the Earth, arc length over angle. I'll let you think about that. We're basically taking the difference in the distance, and then the angle is basically the difference in height over the average distance, between the two locations, basically the midpoint. And that gives us the slight, it's an approximation, but it actually works for small angles just great. So how do we know how much of one model is blended with the other one? Is it 80-20, 10-90? I mean, refraction is also acting, and the surface could also be curved. Well, the best we can do is try to minimize refraction. One of the ways to minimize refraction is to sight in small increments. Don't try to sight way in the distance from example sight 1 all the way out to the target. You'll incur a lot of error. But if you go in small increments, as you see there depicted in the red lines, the air at the end is much smaller. So that's one technique. The other one, as we discussed before, is to look up at steep angles. Now here's a demonstration of upward refraction, just incredible. So I've set the theodolite just 30 arc seconds below. It's kind of easy. The error inside of it is anywhere from 25 to like 29 or something. So anyway, I set it below 90 degrees slightly, so that it's actually level. And looking out through it, look at this apartment building out there, right just to the right of the center. You see that? We're aligned with the top window. Now here, I'm much closer at Avenue, H. And look at the same apartment building. Wow. We're pointing to the fence, right? Maybe 20-30 feet below where the other crosshairs were. Just incredible. So this illustrates there is strong upward refraction at low grazing angles. So we don't want to measure too far out. We want to go in increments. And another technique is to increase the elevation angle to minimize refraction. And we know that's true from Snell's law. There's a gradient here, so looking straight down is actually the best. And we'll talk about LiDAR and satellite imaging in another presentation. Pronounced refraction at low grazing angles is responsible for the mirage, and also look how the cars appear to go behind the curve. Just incredible. This road is extremely level up until a few miles out, and then it slopes up. Notice all the cars. And this poses a constraint on the elevation angle that I was able to measure. The aqueduct is a much better location for this types of measurements, but before going there, I decided to do one more set on a better day and much quicker. Looking at the same targets there. Very clear. It's about 43 degrees outside according to my car's thermometer. And there's hardly any wind. And the target is clearly visible without a lot of turbulence. So 880630. I filmed this with my cell phone through the optics, and sometimes it doesn't quite focus, so I apologize for this blurry image. Visibility was excellent that day. Minimum turbulence. I could really align it to that building very well, and So here's the reverse measurement. We have to do that to find the misalignment error inside the theodolite. The results came out almost perfect. Have a look at this. Wow, just incredible. And I was able to achieve everything in 1 hour. I started at 8:25 and finished at 9:25, and I went in a consecutive order. Just perfect. The combination of a beautiful day with less turbulence and also paying attention to details and the height of the theodolite produced these incredible results. You noticed I have a H adjust column, and at site 1 I was about 3 feet below the road, and at site 2 slightly above, about a foot above the road. Now notice the curve is curving down. It's not a straight line, and that tells us the direction to pursue the flat earth. Unfortunately, I couldn't do that along this road, so I decided to go back to the aqueducts and this time look at steeper angles. I chose Cummings Mountain as my target, clearly visible in the distance. Since I'm measuring at elevations about 1.3 degrees, which is lower than 3 degrees, where I estimate the radius of the Earth is about just right compared to the accepted value, I expected to measure a smaller radius of the Earth. And that sort of came out of the measurements, but something else occurred. A transitory result that lasted for 2 consecutive days. When I graphed the data, I noticed this strange inflection in the curve in the wrong direction from what I expected. I began to feel as if reality was toying with me, mocking me. So I decided to go farther out in both directions to really see how this curve plays out. Set number 2 only deepened the mystery. In the top chart, we observed the same curve for sites 1 through 4. Just incredible. This was on a different day, different temperature, yet we get the same result. Very fascinating. In the bottom chart, plotted over the whole range of values, you can see that things look a little bit different when put in perspective. I began to wonder whether this might not be a gravitational anomaly, a local gravitational anomaly. The optical lever in this case is about 34 miles, so it's very sensitive. It picks up the slightest variations in the gravitational vector. Years ago, I visited the Cosmos Mystery Area in South Dakota, and I was just amazed. I was chosen from the group to go up where those girls are standing because I'm fairly tall. And I tell you, when you sit in the disturbed field, you see a bigger distortion than you observe from the outside. From the outside, you can tell they change height slightly. But when you're in it, wow, it is amazing. I remember looking up at the person next to me, and then we switched position. Then I was looking down at quite a steep angle. It just blew me away. I was curious if this gravitational anomaly would persist for yet another day, so I came back to do more measurements. But to my utter amazement, it was gone. What is going on? Now this time I chose to measure 2 targets close together but at different elevations, so I can do a comparison to see if it occurs in one but not the other. And of course it didn't occur in any of them. But the radius of the Earth calculation indicate that the target that has lower elevation angles produces a smaller radius, which is what we would expect. So I decided to do just one more highly precise survey. This was my best data set to date. I paid attention to details and I made small adjustments. I looked at the imagery, and sometimes after I set the theodolite, things move slightly because we are in a earthquake area. And so I made these adjustments. The weather was perfect, no wind, low turbulence. I could clearly see the target, and I felt like this was really good data. By taking the difference between the first and the last point, I calculate a radius of the Earth of 3471 miles. So that's fairly close to the accepted value, but lower. Up to now, we've been measuring in a very narrow range of elevation angles, but there is a whole lot more. Pondering how to increase that angle, I came up with a brilliant idea. Instead of walking to multiple locations and carrying all this heavy equipment, I could go to a single location on top of a hill and survey a number of points along the aqueduct. From the top of the hill, I surveyed 9 locations along the aqueduct. I looked at the cement embankment. My horizontal reference was a distant airport tower, and that helped me triangulate my position more accurately. I chose well-defined features that I could identify, like a pipe holding the ladder going down in the water. And in rapid succession, I went along and gathered lots of data. So the temperature would be constant. I looked at pipes, and I went all the way out at about 0.5 degree elevation angle, from about 7.5 degrees, so a nice spread in angles. But the results were simply disturbing. The measured height along the aqueduct seemed to match the curvature of the Earth, but with a slightly steeper curvature, which makes sense because water has to flow downhill. That just blew me away. I said, what in the world? Now I had to adjust some values slightly after looking at the imagery. There is some seismic activity that's present, so I had to record things really quick. But I had to replicate this because I couldn't believe my eyes, so I went back another day. This was an even better data set, very smooth. I was very impressed. It was a clear day, and I thought, this is it. I have to find out what that slope is. So I went to the internet. A quick Google search revealed that the slope of the aqueduct is on average 3 inches per mile. So I went back to my spreadsheet and I tried it out. Here we go. Let's go to the aqueduct slope. Put in 0.25 feet per mile. That's 3 inches per mile. Boom! Look at that. Oh my God, just perfect. I was quite agitated. I said, man, I should have never bought that theodolite. But I'm committed to science, and I was on a mission. And when we're at our lowest, that's when breakthroughs are about to occur. The still small voice whispered, hey, you measured a man-made structure. I thought, yes, that could be it. I don't know why I didn't think of that before. I guess I had heard that surveyors don't really concern themselves with the curvature of the Earth because it's in the noise. But that's only for short distance surveying. But long distance like the aqueduct, they have to. So then in desperation, I devised my last experiment. I decided to measure the water level in the aqueduct and walk downstream. And what do you think we're going to find? Think about it. Do you think it's case 2, where the water level is constant, which is what we would expect? Do you think perhaps maybe it's higher or perhaps lower? I didn't know what to expect. I said, wow, it has come to this. Unbelievable. I didn't trust what I was seeing with my eyes anymore to the theodolite. I said, is it refraction? Is gravity bending? Are we in curved space-time? I was really troubled, and it was quite a walk. This is the first location, and I move it so the water moves a little bit. See that? Make waves there. There you go. And it's 7 feet and 2 inches. It was a beautiful day, and the walk seemed to take forever, but I had a lot to think about. How I got started. Was it possible to defeat the globe illusion in the visible spectrum? It was a walk of faith. It seemed like the forces of evil were all around me, trying to discourage me, whispering doubts. As I came around the first bend and measured the water level, it wasn't going down that much, and I really started getting worried. What's going on? But the cement embankment can actually change slightly because there is this phenomena of submersion. I looked it up on the internet. Some of these cement plates, they submerge, or I think it's called subsidence or something like that. So I thought, plus they're not exactly perfect where they round off. So the level was about 7.1.5. So I thought, okay, maybe it's sort of going down, but I expected it to start dropping a lot more quick. Moving along, I found a surveying mark, and the numbering kind of spooked me. It seems like I'm being haunted. The more I walked along, the more uncertain I began to get. I wasn't sure what I was going to measure. I was very curious. What would I measure? What's the water level? If the water level is lower, I could understand. If it's about even, it means it's flowing at what they projected, about 3 inches per mile. But if it's higher, and it would have to be higher for the flat earth. And I thought, oh no, just looking at it I could tell it's not coming up. Maybe it should come up and go over the banks. And by just looking at the aqueduct, that's clearly not the case. There is also algae and deposits along where the water level sits on average. And so it doesn't change much due to, flow rates. And so I thought, yeah, this thing is following exactly the slope of 3 inches per mile. And so I think it is case 2. Almost there. This is the pump house. I'm walking for science, folks. Resignated to defeat, I approached the pump house, wondering where am I going to find. And then a glimmer of hope. The water level appeared to be significantly higher. Okay, so we're by the pump house now. Here's the pump house. Right. And yeah, we were, boom, this was the most distant point. And I used to aim around here. Gosh, the sun is shining. There we go, right there. You see that? I'm moving in the water. There you go. About 6 feet. Right at the curvature. See that? About 6 feet. The water level has come up, folks. Case number 1. You win. Unbelievable. A foot and 2 or 3 inches from over there. Yeah, very, very interesting. So yeah, this the cement was surveyed, laid out to follow the curvature of the earth, and the water doesn't care about that. The water is like, you can do whatever you want. I'm obeying the laws of gravity. And, there you have it, folks. This is incredible. Just incredible. The earth is truly flat. Unbelievable. But yet there is an optical distortion, right? Light bends up because there's a gradient. Temperatures are warm across the surface, but it's not only that. It's also the proximity to a large mass, which is the Earth. Okay, it's the curved space-time. And things move faster, closer to large objects, slower. And in future videos, I will show you that phenomena as well. I have drones, and I'm going to go up in the sky with a drone, and we'll do really fine measurements of Doppler variation. And yeah, exciting times, folks. The Earth is truly flat. You can bank on that. It looks flat at steeper angles, but at shallow angles, not. And they chose to measure the radius of the Earth at shallow angles. Bad scientists, bad. That's what happens when you don't think everything through, and you don't revisit assumptions made in the past. But they know. I know they know. And they're covering it up. They don't want humanity to wake up to the fact we live under a dome. And, holographic universe. It's a backdrop created by the Almighty. They're watching us right now. Hello, I'm here. With renewed hope, I returned to the aqueduct to make my final measurement, looking at the water level. In retrospect, this was a no-brainer. I can't believe I didn't think of that. And I tried to be as precise as possible and also corrected the data slightly in post-analysis of the water level that I was set to. It's kind of tricky because the cement gets wet a little bit and there's reflections, and sometimes I'm not quite pointing it where I should. I also kept track of the temperature, and overall I felt this was a really good data set on a very clear day with very little wind, if any, and the results were just simply shocking. The water level was dropping along a slant dictated by 3 inches per mile, so in about 2 miles it's about 6 inches. I plotted this data based on the aqueduct distance along the aqueduct, not direct line of sight. just incredible, folks. But wait a second, how can this be? The water is going to spill over the banks. They use gates to reduce the waterhead periodically, folks. Just incredible. While I was out there, I had a chance to talk to an aqueduct worker, and he gave me some interesting information.
That stuff RTU?
Yeah, the stuff is the reading on the outside. We have marks on the wall, like every foot.
Yeah.
And we have divided in tenths. So every foot is divided in tenths, and that's how we read the water elevation. So this is the upper stream, which is before the gates.
Yeah.
And downstream is after the gate.
I see upstream and downstream. Yeah.
And so I read 39.8, and then below the gate is 39.0. So the gate is open 2.2.
Yeah.
2.2. So the water is going under the gate.
Yeah.
Pushing under the gate.
Yeah.
And this is the same reading, but this is through the electronic sensors. This is the electronic sensors. So they are close to the real thing outside. They are like a little bit off. I called the office and they don't listen to me. I told them this is what I see, a real thing.
Yeah.
And they say, oh, don't worry.
Because they look at the electronic data, right? So they don't believe you.
No, they don't believe me. They say, oh.
So I had a great discussion with this person, and we chatted for quite a bit, but I decided to plot the data off of his spreadsheet there, and look at that. The WSC is the water surface elevation, okay? And so I took the miles and the normal. So it's the normal where the water, they're thinking it should be on average, but they operate this aqueduct under different conditions, and sometimes the water level can be higher. One other guy I talked to on a different occasion was telling me how there's a delay of like 15 minutes when they open gates before it propagates, and there's diversion areas for water. There's some lakes, and it's quite a fascinating, system. So anyway, I gained a lot of insight, and it finally started to make sense. They're using these gates to, control the water. Otherwise, you're gonna have some real issues. So there you have it, folks. Just incredible developments. I hope you've enjoyed this presentation and have gained a new perspective on this incredible aqueduct. It's quite an interesting construction. The more I read about it, the more impressed I am. It's quite vital to Southern California and other communities. It brings water, much needed water. So what do you know? The flat earth is there. Just incredible. Make sure you folks subscribe and have notifications enabled, because I am planning a lot of videos. I just can't wait to get into space imagery and other things. I am loaded with information, and when I get time, slowly I'm going to put out more videos. These are exciting times, folks, very exciting. He that sitteth upon the circle of the earth will open the dome soon. The Bible says the heavens will roll away like a scroll, and every eye shall see him. I hope you are ready for that event, folks. Just incredible. The earth is incredibly flat. Just unbelievable.